In this video, we are going to explain about a project titled Motion Pattern Classification on Online or Active Data. So now coming to the introduction part, Motion Pattern Classification on Online or Active Data represents a pioneering approach in data analytics, catering to the demand for real-time pattern recognition in dynamic systems. By deploying advanced machine learning algorithms on streaming data, this research area enables immediate insights and dynamic decision making across a wide range of applications. As technology continues to advance, this field is poised to revolutionize various domains, making systems more responsive, adaptive, and intelligent in analyzing and classifying motion patterns. The key challenge in this field lies in developing efficient and scalable algorithms that can handle the high-dimensional and streaming nature of online data. These algorithms must be capable of processing data in real time, minimizing latency, and ensuring robustness against noise and uncertainty. So now coming to the objective part for this project is to develop advanced algorithms and machine learning techniques that can analyze and classify dynamic patterns in real-time data streams. By achieving accurate and efficient pattern recognition in online environments, this research area aims to revolutionize various domains and enable intelligent systems and applications to operate dynamically and adaptability in response to real-world motion patterns. Motion patterns captured by sensors or generated by dynamic systems are subject to various sources of noise and perturbations. The algorithms must be robust enough to handle these uncertainties and still maintain accurate pattern recognition capabilities. So now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirements. In hardware requirements, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDEL, that is 3.7 version is required. So now coming to the methodology part, first upload ship motion dataset. This initial step in this process is to upload the ship motion dataset, which contains data related to ship movements such as roll, pitch, yaw, and accelerations. This dataset is crucial for training and evaluating various algorithms that aim to predict and classify ship motion patterns. Second, pre-process dataset. Once the ship motion dataset is uploaded, the next step is to pre-process the data. This involves data cleaning, normalization, and feature extraction to ensure that the dataset is in a suitable format for training and testing the algorithms. Third, run SVM algorithms. Support vector machine, that is SVM algorithms, are employed to classify ship motion patterns based on the pre-processed dataset. SVM is a popular machine learning technique used for classification tasks. By running SVM algorithms on the pre-processed data, the system can identify and classify different types of ship motion based on their characteristic patterns. Fourth, run random forest algorithm. The next step involves running the random forest algorithm, which is an ensemble learning technique that combines multiple decision trees to make accurate predictions. In this context of ship motion classification, random forest can effectively handle complex patterns and provide robust predictions. Fifth, run CNN algorithm. Convolutional neural network, that is CNN algorithms, are employed for the prediction of ship motion patterns from image data. CNNs excel in image-based tasks due to their ability to learn hierarchical features from data. Sixth, run RCNN algorithms. Region-based convolutional neural network, that is RCNN algorithms, are used to detect and classify specific regions of interest in ship motion images. RCNNs can accurately identify and localize objects or patterns within images. Seventh, comparison graph. After running the SVM, random forest, CNN, and RCNN algorithms, a comparison graph is generated. This graph visually represents the performance and accuracy of each algorithm in classifying and predicting ship motion patterns. The comparison graph provides a clear overview of the strengths and weaknesses of each method, aiding in the selection of the most suitable approach for the specific ship motion prediction task. 8. Predict motion from test image. Finally, the system uses one or more test images to predict the ship's motion patterns in real-world scenarios. The algorithms are applied to the test images and the predictions are generated based on the learned patterns from the training phase. So now coming to the execution part, to execute the project, first we need to open the code folder. So here we have a folder named as PyCatch. In this we are containing a Python file which is containing the Python script in it. Another folder named as dataset. In this we are containing a dataset over here, that's .csv file. Another folder named as images. In this we are containing some images over here. And the folder named as model. In this we are containing some .npy files and .hy files which contain the deep learning algorithms information. These .hy files can be loaded into the project code during runtime to utilize the trained model for various tasks such as making predictions on new data or performing specific operations. Another folder named as test images. In this we are containing some images over here for testing. And here this CNN train, custom button, dataset, tall images and main. These four are the Python files which are containing the Python script in it. And here this is the main Python file over here. This is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. Now to run the project, double click on run.bat file to execute the project. So here this is the graphical user interface. With this we are interacting with the program. Now click on upload ship motion dataset button to upload the dataset images. So here I am selecting this images folder over here, and now click on select folder button to load images for getting the output. So here on this screen dataset loaded, and now click on pre-process dataset button to read each image and then apply HOG and canny and then split dataset into train and test. So now here on this screen we can see image after HOG processing, just the images are processed properly. And now closing this image. On this screen dataset contains 360 images and 288, that is 80% images are used for training, and 72, that is 20% images for testing. And now images for train and test is ready. And now click on run SVM algorithm button to train SVM for getting the output. So now on this screen you can see that SVM got 86% accuracy, and in confusion matrix graph we can see output of 6 zigzag images. 4 are correctly, which are correctly predicted, and 2 are wrongly predicted. And you can see prediction for other classes also. So now closing this image. Now click on run random forest button to get the output. So here you can see that the result for random forest, with random forest also we got 86% accuracy, and we can see correct prediction of all 3 classes. And now closing this graph. Now click on run CNN algorithm button to get the output. So here on this screen we can see that CNN we got 97% accuracy, and in confusion matrix all images are correctly predicted and only one image is wrongly predicted. So now closing this image, closing this graph. Now click on run RCNN algorithm button to get the RCNN output. So here on this screen RCNN we got 58% accuracy, as its accuracy is low. So in confusion matrix graph we can see some predictions are wrong. And now closing this graph. Now click on comparison graph button to get the graph. So here on this screen now you can see that here x-axis represents algorithm names, and for each different color bar represents accuracy, precision, recall and F-score, and in all algorithms CNN giving better result. So now closing this graph also. Now click on predict motion from test image button to upload test image and classify movement. So here I am selecting suppose this first image, and now click on open button to get the classification result. So here on this screen you can see that screen movement is classified as looped, and now you can test with other image. Suppose here I am clicking on another predict motion from test image for uploading the another image. Suppose I am selecting the second image, and now click on open button over here, and you can see again that the ship motion predicted as looped over here. So now closing this graph, and now coming back to the conclusion part. In conclusion, the remarkable progress made in motion pattern classification on online or active data underscores the significance of real-time pattern recognition in dynamic systems by enabling immediate and accurate classification of motion patterns from online data streams. This research area contributes to more responsive, adaptive and intelligent systems that can thrive in real-world scenarios. Moreover, in industrial automation, the real-time recognition of motion patterns can improve process efficiency and safety by promptly identifying deviations or anomalies in dynamic systems.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.